In this video, we're going to talk about transforming and combining random variables. So remember, our random variables are capital letters like X or Y, and whatever value that random variable can take has a corresponding probability distribution. And so what if you wanted to manipulate that probability distribution by adding or subtracting something to it? So it's going to have a lot of the same effects as we studied earlier in the year. So let's say we want to add or subtract some constant A from a random variable. How it changes, or what it changes, really, are measures of center and location. So that's our mean, median, and our quartiles and percentiles. It's not going to change variability, which is range, IQR, and standard deviation, and it's not going to change the shape of the probability distribution. So now let's take a look at an example of a reason why you might want to add or subtract a constant from a probability distribution. So let's talk about scaling test scores, which I'm sure you're very well aware of as a student. So the problem says, in a large intro stats class, the score X of a randomly selected student on a test that's worth 50 points can be modeled by a normal distribution with a mean of 35 out of 50 and a standard deviation of 5, also out of 50. Due to a difficult question on the test, the professor decides to add 5 points to each student's score. So let's make Y the scaled test score of the randomly selected student. So let's describe its shape, center, and variability of the probability distribution of Y. All right, so there's going to be no change in shape, and we know it is approximately normal. It's a normal distribution, so we would say the shape is still approximately normal, no change. The center is going to change, and if it is going up by 5, so center is going to be our mean, so 35 is going to go up by 5, so we can say the mean of Y, which is the scaled score, is the mean of X plus 5, and so that's 35 plus 5, which is 40, so that means that the average is going to be 40 out of 50, not bad. And then the variability, that's not going to change. So the variability is our standard deviation in this case. So the standard deviation of Y, which is the scaled score deviation, standard deviation, it's going to be the same as the regular one, which is 5. And now you may be wondering, well, what effect does multiplying or dividing by a constant have on a probability distribution? Well, let's look at multiplying or dividing each value by a random variable by the same positive number b. So most things are going to change by that value, whether we multiply or divide by that value. So center and location are going to change. So that's our mean, median, quartiles, and percentiles. And our measures of variability are also going to change by that same value b. That's range, IQR, and standard deviation. The only thing that does not change is the shape. And so this graph example down here represents that scaled test score example, but instead of adding 5 to each raw score, the professor decides to double or multiply by 2 each raw score. So notice that the shape doesn't change. This guy is still approximately normal, so is that guy, although it's a little shorter, that's okay. The center doubles, it goes from 40 to 80, and the variability doubles as well, it goes from 5 to 10. Now let's put all those operations together in another example, and it's the baby in the bathwater. Can't seem to escape babies this chapter. So the problem says one brand of baby bathtub comes with a dial to set the water temperature. When the baby safe setting is selected and the tub is filled, the temperature X of the water in a randomly selected bath follows a normal distribution with a mean of 34 degrees Celsius and a standard deviation of 2 degrees Celsius. So let's let Y be the water temperature in degrees Fahrenheit for a randomly selected bath. And remember, in order to get Fahrenheit from Celsius, you multiply the Celsius by 9/5 and add 32. So let's first find the mean of Y. So what I do is, in order to find my mean of Y, I'm going to multiply the mean of X by 9/5 and add 32, which is a transformation of that equation. And so 34 Celsius is my mean, and in order to translate it to Y, multiply by 9/5, add 32, and I get 93.2 degrees Fahrenheit. So that is the mean in terms of Fahrenheit. Next, let's calculate and interpret the standard deviation of Y. So the only thing I need to do with the standard deviation of X is multiply by 9/5 to get the standard deviation of y. And if the standard deviation of x is 2, 9/5 times 2 is 3.6 degrees Fahrenheit. And what does that mean in context? It means when the dial is set on baby safe, the temperature of a randomly selected bath typically varies about 3.6 degrees Fahrenheit from the mean of 93.2 degrees Fahrenheit. So now let's shift gears from transforming random variables to combining them. So that is when we have two random variables. Let's call it capital X, capital Y. And so what if we wanted to add or subtract the mean or expected value from those things? It's pretty self-explanatory, but we're gonna go through it. So all you gotta do, if you want the mean of the sum, you just add up the mean of X and the mean of Y. And now you would do the same thing, but keeping in mind that order of subtraction is important, just like when you subtract anything, random variables or otherwise. The order matters. Doesn't matter in addition, but it matters in subtraction. So if the sum is you add both means up together, the difference is going to be one mean subtracted from the other. But you need to be careful if you are defining the difference as x minus y, then obviously x has to go first. Another thing that we can combine is the standard deviation of the sum or difference of two random variables. But in order to do that, we need those random variables to be independent of one another, which means that if knowing the value of x doesn't help us predict the value of y, which means that x and y are independent random variables. So when we have the sum, or to find the standard deviation of the sum of two independent random variables, we first have to find the variance. So the variance, remember, is our standard deviation squared, essentially. And so that, if we are taking x plus y, and they're two independent random variables, you just add the variances together. So the variance of x plus the variance of y. And then in order to find the standard deviation, we take the square root of that variance. So those two things added up together, take the square root. Pretty much standard deviation. Fun little note here is that this variance is sometimes referred to as the Pythagorean theorem of statistics because it looks like the Pythagorean theorem. But just as the Pythagorean theorem only applies to right triangles, this Pythagorean theorem of statistics only applies to independent random variables. So I guess keep that in mind. Also, fun fact, standard deviations do not add. So don't just add the standard deviation of x plus the standard deviation of y. That's wrong. And so now for the standard deviation of the difference of two independent random variables, you might think, well, if we add the variances, why wouldn't we subtract the variances? It doesn't quite work like that. So when we subtract two independent random variables, the variances actually add. And that's because there's more variability in the values of the difference, which is d here, than in the values of x or y alone. So that should make a little bit of sense only because the variation in x and the variation in y both contribute to the variation in the difference. So all you gotta do is add up the variances. So essentially the sum, variance, and standard deviation end up being the same for subtracting or finding the difference. Now let's put those ideas into practice and talk about two people's Jeep tours that they give in very popular tourist locations. So their names are Pete and Aaron, and they run two separate companies, but we're going to compare them. So the problem says that Pete charges $150 per passenger, and Aaron charges $175 per passenger for their Jeep tour. Now, let's define C as the amount of money that Pete collects and E the amount of money that Aaron collects on a randomly selected day. Why C for Pete? I'm not sure. But here's what we know. The standard deviation of the amount of money that Pete collects is $163.46, and for Aaron, it's $165.03. You can assume that these two random variables are independent. So we're going to define D as the difference between the amount of money that Pete makes, subtract the amount of money that Aaron makes on a random day. And we know that the mean of that difference is $20. Let's calculate and interpret the standard deviation of D. First things first, gonna find the variance of D, or the difference of that. And what I do is I take the value of the standard deviation of C and I square it, and I take the same thing with the standard deviation of E, and I square it, and I add those two things together, and I get almost $54,000. And if you were guessing that I was going to take the square root of this, you'd be right. So let's do that. So when I take the square root of that value, I'm going to find the standard deviation of the difference between the money they collect on any given day, and that value is $232.28. So what does that mean? That means that the difference of Aaron subtracted from Pete's money in the amount collected on a randomly selected day typically varies by about $232.28 from the mean difference of 20 bucks. That's going to do it for this video. Me and my carousel pony friend here are going to go on our own Jeep tour, and we collectively say thanks for watching.